Okay, so this is to continue lecture from the fire alarm that happens. So this is the last example I wanted to do. Actually, it was number 11 in chapter 2. Because this is really difficult to actually do. Very simple to write it with convolutions. Because, well, all you need to do is write f star something. So I want to talk about doing it with convolutions, like just so you can always get a solution. That's kind of the point of convolutions to begin with. They always give a solution, and then I'll basically set it up to actually solve it all the way through. Maybe I'll go through it if I have the energy, but or maybe I'll probably go through it, but it might get really messy. But I also have the work for it here, which I'll send as a PDF. Yeah. So the problem is basically to solve this equation where f is this weird piecewise function with zero initial conditions. And well, the first part of the problem is to actually just rewrite f using Heaviside's first, because that's how we're going to take the forwards Laplace transform of the equation at the end of the day, if we don't use convolutions. So first thing is to talk about writing a function with Heavisides. So what we always do is just take each piece. Like for example, here are pieces like t minus 1 squared, 3 minus t, 0 you don't really care about, that's just 0. And then look at when it turns on, and also when it turns off. Right. And all we do is basically add on all these pieces turned on and off. So like, how we always do is take the function. So here is t minus 1 squared. Sorry. Right, t minus 1 squared. And multiply that to a Heaviside that turns it off, subtracting off the Heaviside that turns it... Sorry. Multiply it to the Heaviside that turns it on, subtracting off the Heaviside that turns it off. So the Heaviside that turns it on, ut minus 1. What turns it off? Minus u of t minus 2. Okay. And do the same for the other pieces. So we have also a 3 minus t times u of t minus 2, because that's when that one's on. It turns off at t equals 3, so we have a u of t minus 3 that we subtract off. So it's like this turns it on, and then this kills it after t equals 2. Right? Turns it on, that'll turn it off at t equals 2. This turns it on at t equals 2, that turns it off at t equals 3. And these are the pieces that we want to turn on and off at those respective times. Right. So that's our f. We're only going to really use it for the non-convolution way. But for the convolution way, I mean, that's... You just need to stockpile this. Okay. So, I guess save some board space for C. Let's basically solve it. So first, always forwards transform. So take the Laplace transform. Right. So we have 0 initial conditions. So that means that the left-hand side, this becomes s squared capital X of s plus x of s equals whatever the heck this is. We don't really care. So let's just call it big F of s. It would be the transform of this, but we don't really need it for a convolution perspective. Okay. Right. S squared x of s is that's the transform of the second derivative. Again, because the initial conditions are 0. X of s is just a transform of little x. Okay. Right. So we're going to use convolution. I guess using convolution. First thing we do need to do is isolate x of s. Colon, I guess. So we do need to isolate x of s first, though. So x of s at the end of the day, well, this is really x of s times s squared plus 1. So we're going to have 1 over, s squared plus 1 times big F of S, right? That's what our big X would be. And, well, this is the nice part of convolution. That's a product of two presumably simpler Laplace transforms, right? So what we want to do is that when we invert it, it'll be the inverse Laplace of this convoluted with the inverse Laplace of big F, right? So I guess to cite the theorem by theorem 6.3.1, right, x of t is going to be the inverse Laplace of this convoluted with the inverse Laplace of big F. Well, we already know that's little f of t. It's like we just took this little f, did it forwards and backwards. That was the forwards, and then the backwards is just the same thing again. Right? That's why some of the problems say like you don't even need to bother computing some of the Laplace transforms because we're just going to invert it at the end of the day. I think C 6.3.9, which we did in class. Right. So we know f. Technically, it's this behemoth of a thing. We just need this. Inverse transform of this. Well, this is perfectly the sine one, where this is like omega squared is 1. That's our omega already. So this is sine of t convoluted with this f of t from here. Okay. And if we want to write this as a definite integral, we can go from 0 to t. Let's not stick the t minus tau to f because of the heavy sides. I would recommend that in general. If you have a heavy side, don't stick the t minus tau one to it. Remember that, well, I'll add it on at the end, but remember that f star g equals g star f. So let's stick the t minus tau to the sign, and then just keep f as a function of tau, and d tau. Right? Or like sine of t minus y, f of y dy if you want a different dummy variable. Right? And again, order doesn't matter because we have the property that just to put on the side, f star g equals g star f. So basically that just lets you freely put the t minus tau one to the more expedient function. Okay. And right, this would technically be an answer, and there's nothing wrong with it technically. Of course, unless a problem says you can't leave it as a definite integral, then you'd have to manually do it all out. Okay, so right, that is it with using convolutions. Right, very simple. If we don't use a convolution, it becomes complicated. So, without convolution, what we basically need to do is compute this big F. Okay. Then we have to divide that by that s squared plus 1 again, and then take the inverse Laplace transform of all the terms. So finding this big F of s is the difficulty. So, right, let's box our little f of t. This was it. That's what we had. So that's what we're going to have to inverse transform. Since they all have heavy sides, what we have to do is use that second shifting property that we need all the terms to have the same shifts as the heavy sides. Okay. So first we need to rewrite it. So t minus 1 looks actually okay on its first term. There's two terms with the heavy side of t minus 2, so let's save that for the end. And then we have this one. So we have minus, we have minus 3 minus t u of t minus 3. Okay. And then now let's include all the u of t minus 2 heavy sides. So we have 3 minus t minus t minus 1 squared. Okay, so these are already correctly shifted, right? Those are already the same t minus 1 shifts for that one, and a t minus 3 shift for that one, almost. If we distribute the negative, we're fine. Right. So, okay, so let's rewrite it one more time, I guess. So we have a t minus 1 squared, u of t minus 1, and then let's absorb the negative sign there, so it becomes a plus t minus 3 u of t minus 3. So that's why that term is actually pretty perfect. And then we have this term. So actually, if we square this all out and do all the algebra, what we get is negative t squared plus t plus 2 u of t minus 2. I hope I was probably blocking it. So, right, we distribute the negative here into the 3 minus t, so that's why it becomes a t minus 3, and then that's why this becomes like a perfectly shifted term. The t minus 1 was fine. This is what happens after we compute all of this. Square this out, add it all together, or I guess subtract it. This is what amounts, right? And this is the headache. Right? We need this shift of t minus 2. That's like not even close. So that's the issue here. Yeah. So what we have to do is kind of like similar to what we did before in like certain backwards transforms. We have to impose a shift. So we have to impose the t minus 2 shift here. So what does that mean? I want to write this. I guess I should copy everything again. Minus, right, plus t minus 3. And then here's where things get interesting. So everywhere we see a t, put in a t minus 2 and then add the 2 back. So what are we going to get? Okay, so here we have a negative parentheses t minus 2 plus 2 squared. Right? That really does nothing, but it makes it look like a shift. And then here we have a plus t minus 2 plus 2 for that guy, and then another plus 2 at the end. So this t minus 2 plus 2, that was really for this middle t. Plus 2 is at the end. And then, oh, darn it. And then u of t minus 2. So just to save some space, right, this plus 2 plus 2, that's going to become just a plus 4. And then u of t minus 2. Right. And now we can finally take a forward transform of this. So, using the shifting property on all of these, what do we get for f of s? First two are the nicer ones, I suppose. Right, okay. So, in the forwards, all the Heavisides do is create an exponent in front. So for example, this one gives us an e to the negative s, and what we're really left to do is transform the unshifted thing, which is just t squared. This one is similar, but now we have a negative 3s, and we really just have to transform the unshifted t. This one, we have the e to the negative 2s, and we have to transform this without the shifts. So that looks like negative t plus 2 squared plus t plus 4. Okay. Okay, yeah. So that's what that is. At the end of the day, this is just negative t squared minus 3t after it's all squared out and added together. Let me double check that. Pretty sure that's right. Right. Yeah. Okay. So that's basically like the intermediate step of using that shifting property, because that's like pulling out the exponents from the Heavisides. So to come up here, f of s is hence transform of t squared is 2 factorial over s to the 2 plus 3. So we have e to the negative s times 2, I guess I'll keep the factorial, over s cubed, plus transform of t is 1 over s squared, or 1 factorial over s squared. So e to the negative 3s times 1 over s squared. And then this, we have two terms here, right, plus, or I guess minus e to the negative 2s. And then what's attached to that? Well, we have another t squared. Remember, we're taking out the minus already. So that's just a 2 factorial over s cubed, where we took out the minus. And then 3t, again, we took out the minus. That's going to leave us a 3 on the top times 1 factorial divided by s squared. Okay, so what does that mean? Erase this. I might need to erase that. So, well, from what we had down here, x of s equals f of s divided by s squared plus 1. So that means we have to take all these terms and divide it by s squared plus 1. So what does that mean? So that means that x of s is really, oh boy, e to the negative s times 2 over s cubed, s squared plus 1, plus e to the negative 3s times 1 over s squared plus 1, and then plus, or minus e to the negative 2s, and then this one's the same, 2 over s cubed, s squared plus 1, plus 3 over s squared plus 1. So you can kind of, okay, so this is x of s, you need to inverse transform it, and then you get we'd get our solution that'll x of t. Great. So how do we go about actually inverse transforming it? Well, whenever we see something like this, we need to do a partial fractions. So another thing is, you can kind of save some work by doing the partial fractions for these two. Find it for this one, find it for that one, and then we'll take 2 of that one plus 3 of this one. Right? Or I guess this already has a 2, so it's just the same thing. But that's kind of, I guess, one shortcut. So, right, we need to partial fraction all of these guys. Sorry, cut off the parentheses here. And that one and that one. But those are just the same. Right? Okay. So, right, from here on, I think that, right, the worksheet, or I guess not the worksheet, the notes I'll also email out should be sufficient, at least for just seeing everything a little better. But I'll talk about it too. So, right, you can just refer to the PDF now, or if you want to listen to me, do it. You know, by all means. Look. Okay. That was pardon. Okay, so we need to partial fraction these two things. The first, so right, I'll give you the decomposition of it, and then the answer pretty much, because it's more algebra than we are interested in. This already is probably more algebra than we're interested in. So the first term, right, I think, right, I took out the scaling of 2. So I just really looked at 1 over s cubed, s squared plus 1. So So how's that going to decompose? This has to be contributing 3 constants. A over s plus b over s squared plus c over s cubed. And then this one is a quadratic that we can't factor, so that has to have a linear root. So it's, no, ds plus e over s squared plus 1. Okay. And then at the end of the day, what you'll get is that it looks like b and e are 0. So at the end of the day, it becomes, okay, so right, solve it. At the end of the day, it becomes negative 1 over s plus 1 over s cubed plus s over s squared plus 1. Okay, so that's the first one. I guess let's do bullets. Second one, okay, so I guess we can circle that first. Second one has a similar decomposition, but the numbers are slightly different. Now it's only squared, so we'd have an a over s plus b over s squared only, and then plus a cs plus d over s squared plus 1. Okay, that was kind of a bad s. And do the same thing, so for a, b, c, and d, what do we get? Turns out a is 0, so we're just left with 1 over s squared minus 1 over s squared plus 1. Which kind of makes sense, actually. If we just added those together, or I guess subtracted those, we would get s squared plus 1 minus the s squared, so that looks good. Anyways, that's that. So we can use this and plug it into these pieces. And what is the best way to write that? Right, so maybe it's best to come up here. What do we have? Right. So this is going to be quite long, but anyways. So this we have 2e to the negative s. And then, well, if we pull out the 2, it's just the rest of this. 1 over s plus 1 over s squared plus s over s squared plus 1. Do the same with the next term. There's no constant in front, good. Now this one is just a 1 over s squared minus 1 over s squared plus 1. Good. And then the last term, joy. So right, if we take 2 times this one plus 3 times that one, what we will end up with is, okay, there's a lot of terms. So we'll get minus e to the negative 2s from the front, and what we get is negative 2 over s plus 3 over s squared plus 2 over s cubed plus 2s minus 3, or sorry, yeah, 2s minus 3, yeah, over s squared plus 1. Okay. So yeah, that is what it becomes. It's while I'm erasing, or in the middle of it, right? So the 2 times this first one, right? That's why we get the negative 2 over s here, the 2 over s cubed, and the 2s here. The 3 over s squared plus 1, that's where you get the 3 over s squared minus 3 over s squared plus 1 there. So that's how it gets plugged in. And, right, now we're ready to inverse transform. So the one thing to note from problems with Heaviside is that it'll spit out exponents in the forwards transforms, and they just kind of sit there in the whole time. And only in the inverse transform, all they do is just shift our variables, right? So, for example, how do I want to write this? Okay. So, for example, this one. Okay, so now x of t. Okay, 2 is out in front. The exponent is just going to cause a Heaviside shift of t minus 1. It's the same sign, different from the other shifting property, remember. Now, these guys. So, 1 over s, or I guess negative 1 over s, well, the inverse transform of that is just a constant, right? This you can think of as 1 over s plus 0, so the inverse is e to the 0 t, or you could think of it as t to the 0th power. Right, so that's just a negative 1. Okay, plus this one would become t, but it's going to have this shift, this t minus 1 shift. So instead of just t, we're going to have a t minus 1. Something off here? Oh, shoot. Oh, sorry. Right, this is cubed. This is cubed. That's not a squared here. This is a cubed. I bet you guys would have caught me in class. I really wish that fire alarm didn't go off. So that's actually a cube. So that actually inverse transforms to, unfortunately I pulled out the 2 here, so we have to divide by 2. So this would inverse transform to t squared over 2 because we had pulled out the 2 in front. So it would be t squared over 2, but we have to impose this shift. So we have to do t minus 1 squared over 2. And then last term, this one, well, that would be a cosine of t, because w squared is 1. But instead of t, we have to plug in t minus 1. Okay. And that's just for the first term. The next term, we have, okay, this is going to give us a Heaviside of t minus 3. Good. And do the same thing. Except now, we have to keep in mind that this one has a minus 3 shift instead. Sorry if that went off. Okay, so, right, this one now, that one transforms to t. But instead of t, we have to plug in t minus 3 because of the shifting property. So we have the t minus 3 here. Okay, and last term, that becomes a sine of t. Happens that omega is 1, so don't need to rescale or anything. And instead of t, we have to plug in t minus 3. Okay, and do the last one. Yeah, same thing. It's just the last one is, right, last one, just know that it's Heaviside of t minus 2. Sorry, I should keep the minus out in front, not plus. And then transform all of these. They're kind of similar to what we had before though. So this one becomes a negative 2. This one becomes a 3t, but again, instead of plugging in t, we have to plug in t minus 2 squared. That's 3 times t minus 2 squared. Or sorry, not squared. 3 times t minus 2. Because the inverse transform of this one was t. This one, okay, since this one does have the 2, now it's perfectly t squared. But instead of t squared again, we plug in t minus 2 squared. So we have t minus 2 squared. This one gives us the 2s over s squared plus 1 gives us cosine of t. But again, instead of t, we plug t minus 2. And then 3 sine of t minus 2, because that one will give us a sign just like that other one did. And that is our final answer. It's all of this. In some sense, it's like a sum of how like each of the pieces of f affected it, because like these are in some sense capturing the piecewise behavior of f. So that's the busy work for it. Just to display it once. Yeah, hopefully there's minimal errors. I already made an error on a test video I made, but anyways, yeah, see you guys on Thursday.